What if I told you there's a universal language, one that connects the artificial minds we're building in our computers to the fundamental laws of the cosmos itself? It sounds pretty out there, right? Well, that's the radical idea at the heart of a paper called Universality of Neural Network Field Theory by Christian Ferko, James Halverson, and Aaron Mutchler. And it proposes a really stunning new link between two of the most powerful domains in all of science.
And it all boils down to this one kind of wild question. Could the very fabric of reality, the rules that govern particles and forces, have some deep structural connection to the AIs we're building? It sounds like something straight out of science fiction, but this paper argues it's not just possible, it's a mathematical fact.
Now, to really get what they're saying, we've got to first appreciate just how different these two worlds seem. I mean, on the surface, they couldn't be further apart.
So on one hand, you've got quantum field theory, or QFT. This is our best description of what reality is. It's the incredibly complex language of particles, fields, and forces. And on the other hand, you have neural networks. These are tools we invented to learn from data, to do things like recognize a cat in a picture. One is about the fundamental structure of the universe. The other is a man-made tool for pattern recognition. So how on earth could they possibly be related?
Well, that's where this paper comes in. The authors argue there's a bridge between them. They found a kind of Rosetta Stone that lets us translate the language of physics directly into the language of AI. And when you do that, you find a hidden structure they both share. This bridge has a name, the Neural Network Field Theory Correspondence. And the idea is, honestly, pretty astonishing. It says that any quantum field theory you can think of can be perfectly and completely described by a neural network. And I want to stress, this isn't just a good approximation. It's a totally equivalent dual description of the same thing. Okay, so here's the key idea. Think of it like describing a movie. The old-school physics way is what the paper calls output space. It's like watching the final movie. To figure out what happens, you have to add up every single possible path a particle could take. It's complicated. But the neural network way, the parameter space, is like having the director's script. You don't need to watch every possibility, you just need the script, a specific set of numbers, or weights, for the network, and it will generate the exact same story. Two totally different descriptions for the exact same reality. Now, look, this idea wasn't totally out of left field, but its scope was thought to be very, very small. And this is where the paper just blows the doors wide open. For a while now, physicists knew this correspondence kind of worked for really simple one-dimensional quantum systems. Basically quantum mechanics 101. It was a neat curiosity for sure, but most people figured it was a special case that would just fall apart for the more complex theories that actually describe our universe. But this paper proves them wrong. The authors show, with math, that this connection is not a special case. It is universal. It works for every single quantum field theory in any number of dimensions you can imagine.
And don't just take my word for it. Here's the money quote right from the paper. They prove that these mathematical objects at the heart of QFTs, what physicists call tempered distributions, which is really just the formal language for describing quantum fields, can always be represented by a neural network. It's an incredibly powerful, all-encompassing statement.
But the implications of this universal proof? They get even weirder. If you can describe any quantum reality with a neural network, how much information do you actually need to define it? The answer is kind of shocking. It's this. I know, right? A single number. The proof shows that a single random number, like 0.7358 and on forever, known with infinite precision, contains all the information needed to generate the rules for any quantum field theory. A single parameter, just one point on a number line, can encode an entire universe of physical laws. That's an insanely compact way to describe reality. Of course, a bold mathematical proof is one thing. But you have to ask, does this radical idea actually work in practice? To find out, the researchers decided to put their theory to the test. And they didn't pick an easy one either. They chose a notoriously difficult test case called Liouville theory. It's a really complex interacting QFT that's super important for understanding things like 2D quantum gravity. But here's the crucial part. For some of its properties, physicists have an exact formula for the right answer, which makes it the perfect proving ground. And the results are just stunning. This chart here compares the exact theoretical prediction, which comes from this ridiculously complicated thing called the Dose formula, with the output from their neural network simulation. And as you can see, they match almost perfectly. We're talking within just a few % error. This isn't just a theory anymore. This is a practical, powerful new tool for actually doing physics. So, okay, let's just take a breath. We've got a universal mathematical proof and a successful real-world test that absolutely nails it. So what are the big takeaways here? What does this new map of reality actually tell us?
So what's the bottom line? Well, first, we now have a direct translation, a Rosetta Stone, between the language of physics and AI. This gives us an incredibly powerful new way to simulate quantum systems, letting us tackle problems that were basically impossible before. On a deeper level, it suggests this profound link between information, computation, and the physical universe itself. And maybe the most exciting part? It opens the door to training an AI not just to simulate theories we already know, but to search the vast landscape of mathematics for entirely new laws of physics.
And that leaves us with one final, profound thought to chew on. For centuries, we've used math written in the language of calculus and geometry to describe the universe. But now, we know there's another, equally valid language, the language of neural networks. So, if any physical reality you can imagine can be described by a neural network, what does that truly say about the fundamental nature of the universe we all inhabit?